Okay, good. Do you guys have that supplement? Maybe you told to get the supplement. Everyone has some sample problems. Maybe, I'm not sure, let's see. Have you seen anything like looking like this? Well, if you don't have it, then we'll get you a copy, or we'll at least send you the PDF.
Yeah, actually I do.
You have it? Okay, all right. Okay, let's go through this, because this kind of covers some stuff from yesterday, and then this kind of reflects the kind of the new type of questions that they started to ask more recently that are not as much, say, calculation based, but more knowledge based. Okay, so you see the first one here. This is talking about sampling. So load settlement behavior of an in situ deposit will be determined from laboratory odometer testing. It's the consolidation test. And the type of soil specimen that will provide the most reliable load deformation characteristic is a soil sample obtained from, 4 types of samples. So a thin-walled push sampler or Shelby tube, SPT, standard penetration test sampler or split spoon sampler, trimmings from a hand auger or trimmings from the outside of an auger. Okay, so, this is the consolidation test. This is one where you take the little sample and then we're going to take measurements as we put load on it. So you really need to have a good quality sample. Okay, so here you can see that 4 types of ways to get a sample. I mean, even if you didn't know anything or didn't know that much about, say, you didn't know what a Shelby tube sample was or something, and maybe some people are maybe a little less familiar with Shelby tubes. But you look at standard penetration test sample, that has a lot of energy and it doesn't give you a good quality sample. Trimmings from a hand auger, I mean, that's already loose material from a hand auger. It's very messed up and you can't really get good samples from that. And then trimmings extracted from the outside of an auger. Well, that's the stuff that's the junk that comes up from the outside of the auger. It's all disturbed. So the thin wall push sample, and the Shelby tube has a very thin wall and it's pushed into the ground. So when you extract it, it's pretty much fairly undisturbed sample that you get. So that gives you that should be the most reliable type of test. So A. Okay. Here, we didn't talk about other methods of subsurface exploration, and this kind of gets into it. Okay, borings performed on a site indicate subsurface profile consists of 30 feet of silty gravel underlain by interbedded claystone, sandstone bedrock. Which of the following exploration techniques is the best choice to provide an estimated shear wave velocity for the soil and rock profile? Okay. Kind of the words might give you the indication what the right answer would be here. Because if you want shear wave velocities, a pressure meter is a device where you put into the ground and you apply pressure to it and it kind of measures the resistance of the soil that is exerted on the pressure meter. So it gives you an indication of what the lateral stresses are. It's good for determining like coefficient of earth pressure, for coefficient of at rest. So a K naught value. So it doesn't give you anything about shear wave velocities. Let's go to C, ground penetrating radar. Well, GPR is mostly used for really trying to identify utilities. It's kind of limited in how far it can go. It doesn't tell you anything about shearing velocities. Electrical resistivity, that's just good for looking at the resistance of the soil. Maybe you would be using it for corrosion type purposes. Seismic refraction, that's a method where you do a survey on the ground, you put accelerometers on the ground, you get a source for the energy, and it measures the time it takes for seismic waves, P waves and S waves, to travel through the ground and return to the receivers. And if you have a layer at depth, like such as that bedrock interface, it will travel down to that layer and then travel back up. So it will give you a good indication of what that is. So seismic refraction would be that method. Okay, here it talks about standard penetration tests. So usually low blow counts are encountered in the soil, expected to be medium dense to dense. This indication that the following condition is most likely present. Okay, A, sample drive shoe is badly damaged or worn due to too many drivings to refusal. B, cobbles are encountered. C, the sampler drive shoe is plugged. D, the groundwater in the borehole is much longer than in situ conditions immediately outside the borehole. Let's say, you kind of look at some of these answers, it doesn't really, the only real logical one is number D. It says groundwater. Usually if you're driving below water with the, sometimes these are used in casings or hollow, since we use hollow stem auger a lot, you're drilling down, and then if you have groundwater that's up higher and the bottom of the casing or the hollow stem auger where you have your sampler, you've got some hydraulic, you have the hydrostatic pressure acting on the bottom of the sampler. And sometimes that pressure is acting up and it can cause your material to essentially liquefy. It will come loose. So you would get low blow counts. And that's one problem in using the standard penetration test and getting reliable values below groundwater. That's why most people would say the best method really would be to use like mud rotary drilling, because with mud rotary you have the hole that's filled with drilling mud, and that's essentially maintains the integrity of the sample, that you don't get the blowout because of the differences in the atmospheric, the pressure difference between the sample and the air above. So I've seen a few indications where some people predict liquefaction because you get low blow counts, but it's because they just had lousy sampling techniques. Okay. Actually, one of the examples from NCES actually uses the USDA method. And so here you're given a gradation curve. You can see the points where they did the various tests. So probably here, the tests in the circles are probably done with a sieve. The ones down here, we didn't talk about it, but you should see they're shown with crosses. those are probably estimated from a hydrometer type of test, if you know what that is. So, but anyway, you get a gradation curve. So from the gradation curve, you go to this chart. So you got to get the percent. You get the percent of sand, clay, and silt, and then you can see where it falls in this triangle. So the percentages, you can see gravel up there, you got like about 2% gravel. You can see where, at this line here, is where gravel is, and you can see like it looks like about 2%. And then the percentage amount of sand is between here and here. And you can see it's predominantly sand. So something like 18, let's see, that's about 98 minus 18. So about 80%. And then the silt sizes are here to here. Oh, I'm getting feedback from the fan. Silt's here to here, and then clay. So you can get those percentages off the chart. And you can see that you got 17% silt, 1% clay. So sand, 80%. Silt is 17%. And this is silt here. So 17%, something like that. And clay is 1%. That's way down here. So you can see that it's falling in this loamy sand area. So from a USDA point of view, this would be classified as a loamy sand. So on the exam, they probably have to give you the chart, then you have the grain size distribution, then you just go to the chart and you get your grain sizes, and then you go to the chart, find out what area you fall in. Okay. All right. This is, I suspect that this type of problem, this won't be a morning problem. This has got to be an afternoon. This is this is depth. The others might have been breadth. This is depth, and this is particularly talking about rock core drilling. Okay, now, so you have, it says rock core recovered from 160 feet to 175 feet. So it's a 15-foot run. And they say which of the following